We've seen that increasing the constant pressure at which these diagrams, like the one shown here, and I should probably again mark that this is constant pressure, but when we increase that pressure, it pushes these curves outward and upward from where they sit originally. But what happens when we shift them inward? Okay, we did look at this for each of the individual phases, but let's see what it looks like for them as a group. So for both of the solid, which I'm drawing here in a purple curve, and the liquid, which I'm drawing here as a purple curve, they don't stray very far as we move that pressure downward. Okay, and so it does not shift this intersection point very much. We see that happening, basically that phase transition is still happening at roughly the same temperature. But what happens as we shift the gas phase curve down? Okay, in the vapor phase, remember it's a bigger effect, so it's going to shift this outward more. So this would be one possible lower pressure curve that we might see. And we could continue doing this, and eventually we would find that there would be a curve, and I won't shift the liquid and solid curves for this at all, but there would eventually be a pressure at which this would come down, and it would go right through the point at which the solid and the liquid curves cross. What's happened there? All right, at a point here where all three of those curves cross, that basically is implying that the Gibbs energy of the vapor is the same as the Gibbs energy of the liquid, which is the same as the Gibbs energy of the solid. So basically all three of these phases are in equilibrium. Now what does that mean? Well, it means that all of those phase transitions now are possible. All of them can occur at this same time. What we have defined here for this particular pressure, so let me mark this as a particular pressure, and that'll be the same, let's say, for both the solid and liquid. At this particular pressure, we'll call this pressure TP, where TP is triple point. And the triple point is the point here where all three phases are in equilibrium at the same time. So it represents the conditions under which all three phases coexist, and they will be in equilibrium. Okay, well that's kind of an incredible place. So you find solid, liquid, and vapor all in the same place. Now I'll suggest that you look at some of the videos in the lesson, because at least one of those videos actually shows you what that triple point looks like for a substance. So you can see the solid, liquid, and vapor phases all interchanging at the same time. But I'll note that every substance has a triple point, because you can find a point at which the pressure, I'll call it P sub Tp, and the temperature, T sub Tp, will coincide so that we have a point like this where all three of those phase transitions are occurring at the same place. Now I do want to remark that you do not see this for the molar volume. So in other words, the molar volume of the solid does not equal the molar volume for the liquid at this point, does not equal the molar volume for the vapor. So in that sense, these three phases maintain their identity because they all have different molar volumes. But at this particular point, we do have the case that the pressure and the temperature are the same. Now I want to look at one further thing with this, and that is, what if we have a case where the pressure is below the triple point pressure? So we're looking at a constant pressure that is below the triple point pressure. And again, I'm going to graph the Gibbs energy of the phases versus temperature. All right, in this particular case, I'm going to have the solid curve, coming across like this. I'm going to have a liquid curve coming across like this, and the vapor curve coming down like this. All right, now let me label these so that we know what they are. This is a solid, this is the liquid, and this is the vapor. So we have shifted this curve even farther to the left, so that now there is an intersection between the solid curve up here and the vapor curve. And so a phase transition occurs directly between the two in this case. And this point here represents the temperature of sublimation. So in other words, we're having a direct solid to vapor phase transition that occurs for these things. Now the other thing I want to point out is that we have solid here, it's the most stable phase because it's the lowest in Gibbs energy. And then the vapor, which is the lowest in Gibbs energy, is the stable phase here. The liquid never makes it. So at this particular pressure, we should not expect to see any liquid at all. You may wonder, wow, how can this ever happen? Absolutely. In fact, it happens in a very common substance. If you've ever done anything with solid carbon dioxide, also called dry ice does not melt. It goes directly from the solid phase to the vapor phase. And that's because the triple point pressure for carbon dioxide is at about 5 atmospheres. So in other words, here at regular 1 atmosphere of pressure, we're in this range where we're well below a pressure that is at the triple point. So we have this direct transition that occurs between the solid and the gas, and we never see the liquid. Now, if you want to look at liquid carbon dioxide, what you would have to do is to raise the pressure above the triple point pressure. You'd have to raise the pressure above 5, actually about 5.11 atmospheres. And once you do that, then you would be able to observe liquid CO2. It does exist, but only under those special conditions.